Welcome back to Cosmos in a Pod
Yes, welcome back.
for another deep dive into space and astronomy. This time, we're going all the way back
All the way to
to the beginning of the universe. We're talking about the cosmic microwave background.
the CMB.
Yeah, the CMB for short. So sometimes called the afterglow of the Big Bang.
Mm-hmm.
And yeah, I mean, that's kind of a cool way to think about it.
Right.
But it's so much more than just leftover light.
Absolutely.
It holds so many secrets
It really does.
about how everything that we see came to be.
Yeah.
Galaxies, planets.
Us.
Yeah, even us. So to kick things off, can you just explain what exactly the CMB is?
Yeah, so it really is more than just a faint glow.
Okay.
It's almost like a baby picture of the universe.
Wow.
A snapshot from when the universe was just a tiny fraction of its current age. Like, imagine the universe
Okay.
as a newborn.
Okay.
A baby universe,
Right.
just 380,000 years old. And back then, it was incredibly hot and dense, like a swirling soup of particles and energy. And actually, light couldn't even travel freely.
Yeah.
It kept bumping into all that stuff. But as the universe expanded
Okay.
and cooled down,
Yeah.
things settled down enough for light to break free,
Oh, wow.
to travel across the cosmos. And that first burst of light is what we detect today as the CMB.
So we're seeing light that's been traveling for billions of years.
We are.
That's crazy.
It is.
But how did we even find this baby picture?
Well, you're right. It's not like we can just point a telescope anywhere and see it.
Right.
It took kind of a cosmic accident,
Oh, really?
Yeah.
Okay.
Back in 1965, two physicists,
Okay.
Arno Penzias and Robert Wilson,
Okay.
were working with this giant radio antenna,
Okay.
and they kept picking up this annoying hum,
Oh,
this background noise. They just couldn't get rid of it.
really?
Yeah. And at first, they thought it was interference,
Re-
maybe pigeon droppings messing with their equipment.
Pigeon dropping.
I know.
That's hilarious.
It's a funny story now, but back then, they were completely stumped. But it turns out that this noise was actually a signal from the universe's earliest days.
No way.
Yeah. And it just so happened that another group of scientists
Okay.
had predicted that if the Big Bang really happened,
Okay. Yeah.
there should be this faint afterglow of radiation spread out across the universe.
Wait.
And boom, that's exactly what Penzias and Wilson
So-
had accidentally detected.
So they won a Nobel Prize for basically finding pigeon,
Basically,
Okay. So what can we actually learn from this ancient light?
it tells us so much more than you might think.
Really?
Yeah, it's like a cosmic fingerprint,
Oh, okay.
containing information about the universe's early ingredients, its shape,
Wow.
and even its future.
Okay. I'm hooked. You got me thinking about the universe
I'm glad.
in a whole new way. I can't wait to hear more about what this fingerprint reveals.
Yeah, for sure. Yeah, it really is like a cosmic fingerprint. And one of the biggest things it tells us is that the universe is surprisingly smooth.
Smooth. But what about all the galaxies and stars and planets? It doesn't seem very smooth to me.
Well, yeah, you're right on a small scale.
Okay.
But when we look at the CMB, we're seeing the universe on a much grander scale.
All right.
And the temperature of the CMB is almost exactly the same in every direction.
Wow.
It only varies by tiny fractions of a degree.
Okay.
And this tells us that the early universe was incredibly uniform.
So it was like if you took a giant cosmic blender and mixed everything up perfectly.
Exactly.
Okay, that makes sense. But if everything was so evenly spread out in the beginning, how did we get all the clumps and clusters we see today? How did stars and galaxies even form if everything was so smooth?
Well, that's where things get really interesting.
Okay.
Because even though the CMB is remarkably uniform, it does have these tiny, tiny variations in temperature. We're talking about differences of just a few millionths of a degree.
Wow.
But believe it or not, those tiny variations are incredibly important.
So these almost undetectable temperature differences,
Yeah.
they're the key to the universe's structure.
They are.
How does that even work?
Well, think of it like this.
Okay.
Imagine a perfectly still pond.
Okay.
Now drop a tiny pebble into it.
All right. So you get ripples spreading out from where the pebble landed.
Exactly.
Okay.
And those tiny temperature variations in the CMB are like those pebbles in the pond.
Right.
They represent slightly denser regions in the early universe.
Yeah.
And over billions of years, gravity did its thing. It pulled more and more matter towards those denser areas,
Okay.
and eventually forming the stars, galaxies, and clusters of galaxies that we see today.
Wow. So those tiny, almost imperceptible variations were like the seeds of the entire cosmic web. That's mind-boggling.
It is.
But how do we know all of this is true? I mean, how do we know the CMB is really telling us about the Big Bang and the early universe?
Well, that's a great question, and the answer lies in the details of the CMB's properties.
Okay.
The specific pattern of temperature fluctuations, the fact that the CMB has a black body spectrum, the way it's polarized. All of these things match up perfectly with what we'd expect to see if the Big Bang theory is correct.
It's like a giant cosmic puzzle, and the CMB is helping us put all the pieces together.
Precisely. And the more we study the CMB, the more evidence we find to support this picture.
So it's like we're constantly finding new clues.
We are!
Ooh, like what? Give me some of the big cosmic mysteries.
Well, for one, there's dark matter.
Dark matter. Yeah, I've heard of that.
We know from the CMB that it makes up a huge chunk of the universe.
Okay.
But we still have no idea what it actually is.
Right.
We can't see it directly, but we know it's there because of its gravitational effects
Okay.
on galaxies and the CMB itself.
So dark matter, it's like the universe is in double scaffolding, right? Holding everything together.
Precisely. And then there's dark energy, which is even more mysterious.
Oh, dark energy.
It seems to be accelerating the expansion of the universe, but we're completely in the dark, no pun intended, about its nature.
Okay, dark matter, dark energy sounds like we're missing some pretty big pieces of the cosmic puzzle.
We are, and that's why studying the CMB is so crucial.
Okay.
It's one of our best tools for probing the mysteries of dark matter, dark energy, and the very beginning of the universe.
Right, I'm definitely on the edge of my seat here. So how do we actually study the CMB? I mean, it's not like we can just go out and scoop some up, right?
Well, no, but we can build incredibly sensitive instruments to detect it.
Okay.
In fact, there have been several groundbreaking missions dedicated to studying the CMB in ever greater detail.
Oh, tell me about those missions. What have we learned from them?
Yeah, so one of the most important was COBE, the Cosmic Background Explorer. Launched back in 1989, it was the first mission to really map out the CMB in detail and confirm some of those key predictions about its properties. You know, it's a huge step forward in our understanding of the early universe.
So Kobe was like the pioneer, right?
Mm-hmm.
Paving the way for future missions.
Exactly. And then came WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001. And WMAP gave us an even more precise picture of the CMB, allowing us to measure those tiny temperature variations with incredible accuracy. It was like going from a blurry photo to a high-definition image.
That's amazing. So we were able to see those ripples in much greater detail.
Yes, and that gave us a wealth of information about the age, composition, and geometry of the universe. And then in 2009, the European Space Agency launched Planck, which took things to a whole new level.
Planck, okay. Yeah, that name rings a bell. Didn't it create the most detailed map of the CMB we have?
You got it. Planck's instruments were so sensitive that it was able to detect even fainter variations in the CMB, revealing even more subtle details about the early universe. It's incredible to think how far we've come since those first accidental observations, back in the 60s.
It really is, yeah. A testament to human curiosity and ingenuity. So what's next? Are there any new missions planned to study the CMB?
Oh, there are several exciting projects. On the horizon, scientists are working on developing even more sensitive instruments that could potentially detect the faint signature of primordial gravitational waves. Those ripples in space-time from the very first moments after the Big Bang.
Wow, that would be incredible. It'd be like listening to the echo of the universe's birth.
Exactly. And there are also proposals for new space telescopes that could study the polarization of the CMB in even greater detail, which could reveal even more about the nature of dark matter and dark energy.
So the quest to understand the CMB and the secrets it holds is far from over.
Definitely not. The CMB is like a cosmic Rosetta Stone, providing a window into the earliest chapters of the universe's story, and the more we learn, the more we realize how much more there is to discover.
Yeah, it's both humbling and inspiring at the same time. This has been an incredible deep dive into the cosmic microwave background.
Yeah, it's been a pleasure sharing this journey with you.
To all our listeners out there, I hope you found this exploration as fascinating as I have. If you want to learn more, we've got links to some great resources in our show notes.
And of course, don't forget to subscribe to Cosmos in a Pod for more deep dives into the wonders of space and astronomy.
You can find us on all the major podcast platforms, and be sure to check out our YouTube channel for even more cosmic content.
Thanks for listening, and keep looking up.